Entonces ahora pasamos al segundo tema de este bloque, que se refiere a la inspección de túneles con sistema 3D de alta resolución. El disertante es Jerome Steinkuehler, que es director de ingeniería de la firma Divit, una empresa con sede en Redmond, Washington. Jerome, Master of Science, lideró proyectos exitosos de escaneo de túneles en todo el mundo y recientemente fue el orador principal en la conferencia de excavaciones en Las Vegas en 2021. Tiene un profundo conocimiento del desarrollo de datos en 3D basados en LIDAR y escaneo fotogramétrico. Así que bueno, ahora nos vamos a pasar la presentación que nos preparó. Creo que él está, sí, está conectado y vamos a pasar su presentación.
Hello, buenos dias, and welcome to my presentation. My name is Jerome Steinkuehler, and I'm the Engineering Director of Dibit Measuring Technique USA. Dibit is a worldwide operating company that is specialized in tunnel surveying and tunnel scanning. Our headquarters is in Austria, and we have subsidiaries in the United States and in Australia. Our US office is responsible for the projects here in the Americas. My presentation today concentrates on our latest developments and scan data of high-resolution 3D tunnel inspections. So let's talk about my today's content. First of all, I will give you a short introduction into previous inspection methods and will then talk about the differences compared to inspections nowadays. After that, I will present you our latest 360-degree scan systems, Canon and Altera. Then I will show you some specific tunnel projects that we're currently working on. One project for a highway tunnel, one project for a railroad tunnel, and a project for a water tunnel. And at the end, I will give you a short outlook to what we are currently developing and what our future for improving tunnel scans will be. Okay, so let's talk about the previous inspection methods. Before 3D tunnel inspections has been developed, the work of previous inspection methods is combined with a lot of manual work and high efforts in the tunnel. To detect cracks, the tunnel inspection engineer needs to manually map the cracks, which is not always easy to find them. Furthermore, the survey and mapping of any kind of damages is hardly possible. High efforts like time-consuming work in the tunnel and shutdowns make a tunnel inspection to a long and hard planned process. Most of the inspections take place in the tunnel, meaning a shutdown of several days is mandatory. Furthermore, requirements for manpower are high with a tunnel inspection engineer plus several assistant persons and some more stuff on site. So raw materials and supplies like lifting ramps and closure equipments are necessary to fulfill the inspection requirements. So compared to the previous inspection methods, the demands of tunnel inspections presently are first a fast data acquisition, meaning shutdown times can be minimized, which lead to marginal traffic interruptions. The scan delivers objective and comprehensible data captured of the whole tunnel surface, so 360 degrees. The manpower requirements are marginal compared to previous inspection methods. Due to short shutdowns and fast acquisitions, the inspection intervals can be higher. So they can be like every year instead of every 2 years or even less. The scans can be performed for as-built documentations or inspections or even during construction to collect data of the different construction phases. Our newest development is a measuring system that scans 360 degrees of tunnel surface. Okay, so Dibit developed two 360-degree scanning systems. First of all, the Canon and the Altera. They are both state-of-the-art 3D tunnel scanners. The cannon, which you can see here on the right, which is mounted to a highway truck in a subway tunnel, delivers data with acquisition speeds of up to 100 km per hour. It is a combined hybrid system with a LiDAR scanner, which is at the front of the system, and 10 cameras. These cameras are horizontal and in a helical shape arranged to deliver 360 degrees of coverage. High-performance LED flashlights ensure to illuminate each single picture fully. The cameras can be adjusted to the tunnel diameter to deliver sharp measurement pictures in every setting. Our second scanning system is the Altera, and the Altera is a smaller scanner device that is attached to a pushcart. This device can scan up to 10 km per hour, or let's say walking speed, and it is a hybrid system with a LiDAR and 6 cameras which are arranged horizontally and helically to cover 360 degrees of the tunnel surface. You can see the laser here in the front and the cameras are in the center. The high-performance LED flashlight technology illuminates each picture fully. So the flashlights are here and here. The Altera is specially designed for small tunnel diameters of up to 6 meters, like water tunnels, road ramps, or subway tunnels. So now, after all this technical information, I would like to show you a short video of how it looks like when our 360-degree scanning system Canon operates in the tunnel. So have a look. So I hope that these were not too many flashes for you. Okay, so now let's get to the results. The tunnel scan usually delivers sharp images with a final resolution of 1 by 1 millimeter on the tunnel surface. So that means that deficiencies like cracks down to a crack width of 0.3 millimeters can be visible. The measurement accuracy, meaning the global georeferencing accuracy, is plus minus roughly 10 millimeters. With the help of the scan data, our clients can fulfill an objective analysis of the tunnel features in a virtual environment based on a color textured 3D model, which is used for the digital inspection of tunnels, orthophoto plots, and cross-sections. Dibbit developed this semi-automatic crack detection to redraw cracks accurate and time-saving. But I will talk about that later in detail. The scan data are the basis for quantification of damages like cracks and the inventory of tunnel components like lamps, cables, tracks, or doors. The data can be exported to open data formats like LAS, OBJs, or ASCII point clouds to get comparable results. In Dibbit's proprietary software Dibbit 8, the data management is made in the TIS database, which is the Tunnel Information System database. It is a centralized structured database for various construction stages or inspection intervals. Artificial intelligence, AI, is used to cognitively detect tunnel objects of any kind, like tunnel inventory, lights, tracks, or doors. Now I want to show you some of our recent scanning projects. This here is a short video showing an exemplary road tunnel in Austria in our software Dibit 8. It is the Setzenberg tunnel, which is a highway tunnel located in Austria that has two tubes for each direction, one tube with 2 lanes each and a total length of 550 meters. In this video you can see a 270-degree two-color scan including our TIS objects as in red. On the left bottom corner you can see the 2D orthophoto view, and on the right in the center you can see our 3D view. The cracks were drawn with our semi-automatic crack detection. The scan data resolution is 1 by 1 millimeter on the tunnel surface. These data are in inspection phase, meaning to highlight the tunnel surface, all the geometrical elements like lights and cables have been smoothed out. On the top left corner you can see our TIS database. By switching off and on the database you can switch off and on all the drawn cracks in the tunnel. Now we can have a look from the outside of the tunnel in our 3D view. Dibit 8 shows you the exact location of the tunnel and where you are right now in the viewer on the bottom toolbar. Now let's go back into the tunnel. Here you can see the smoothened geometrical objects, and we switch back on the cracks. The next project I want to show you is a railroad tunnel. This is the Unterstein tunnel in Austria, which is a 300-meter long one-track railroad tunnel, and it is a part of Austria's ÖBB railroad system. In the lower left corner you can now see the profile view. You can switch easily to the object information to every mapped TIS object. Each object is defined by a global position, a length, and dependent on one kind of object, an area. By going along the profile you can see a yellow sign in the 3D view. This is a 360-degree true color scan, and the resolution on the surface is 1 by 1 millimeter. Here you can now see the tunnel walls, and now we go down and have a look at the tracks. The yellow line in the center is the tunnel alignment. This data is also in inspection phase meaning to highlight the tunnel surface. All the geometrical elements like cables on the top have been smoothed out. So now you have a look at the gravel bed, and we go back up to the walls. So now let's go out of the tunnel, and we can have a look from the top. So after showing you a highway tunnel and a railroad tunnel, the last tunnel I want to show you is a freshwater tunnel here in America. So these data show a 360-degree true color scan of a water tunnel in America that has been scanned by our Altera system. The surface resolution is again 1 by 1 millimeter. This scan includes a water-covered invert. This water coverage has depth of up to 15 centimeter. You can see the water-covered invert from here to here. All the data in between have been captured by our scanning system. This screenshot here shows you our 3D viewer in the bottom left corner and our 2D orthophoto plot in the center, including our TIS objects. In the top left corner, you can see the different TIS classes, which are represented by different colors and objects in the tunnel, like construction joints and cracks. After showing you our recent scanning projects, I want to give you a short outlook on what we are working on and our next steps in improving our tunnel scanning that are presented on this slide. First, we are working on an automotive scanning card which shall be used for the Altera to automatically scan tunnels without an operator pushing the card. Our next software steps are improving our AI algorithms to make the automatic detection of tunnel damages and tunnel inventory more reliable and more stable. The implementation of multispectral sensors like thermal cameras can help to find specific tunnel damages and/or water intrusions with thermal images, as you can see on the bottom right corner here. Another big topic is the interface between our TIS database and BIM. We want to connect both to process the BIM objects and combine them into Divid 8. So at the end, I would like to say thank you for your attention, and I hope you liked my presentation about 3D tunnel inspections. And if you have any questions, feel free to contact me. Goodbye.